The graph of sine or cosine function is periodic, or even generally, the graph of any trig function is periodic, meaning it has one base unit to start out with, and the rest of the graph is the replication of the same base unit. So allow me to bring up a demonstration right here. Say when our function is the standard original sine of x, then looking on my graphing device here, then the complete graph of sine of x is here. But really, this complete graph of sine of x right here is a replication, an infinite replication of one base unit, and that base unit is here. And that's the whole reason why we have been calling that it's a period, because we have one period here and the rest is just the replication of that same period over and over, to the right hand side, infinitely to the right hand side, or infinitely replicating to the left hand side. Similarly, when we're looking at our the trig function that we have learned so far, cosine of x, the complete graph of a cosine of x is shown right here in my Desmos graphing device, and the base unit we can recognize here is going to be this small portion of the graph. And once again, that's the whole reason why the whole time we've been saying that cosine has a period being a 2 pi again, because the complete graph of cosine, the actual complete graph of cosine, is an infinite replication of that same portion here and being replicated infinitely many times. And so due to that nature of any trig graph right here, we realize that it is now important to be able to recognize the base units on any complete trig graph. And a lot of time when we have to construct or have to do a hand sketch of any trig graph right here, then as long as we can successfully draw the base units of any trig graph, we're mostly done with sketching the graph of a trig function, of any trig function. And so along with this video lesson, allow me to introduce the concept of the start and the end of the base units on any trig graph. And so fundamentally, as we have seen through a couple of examples of the transformations, and even though we have not completely learning all the transformations yet, but when it's a sine function, allow me to do a hand sketch version here so that it catches the viewer's attention on the learning here a lot faster. But when it's a sine function, what first to remember about the base units, and I haven't gotten into any further details yet, but the first impression about the base unit anyone should now have in mind, or at least after this that I'm pointing out right here, that the base units on the sine function has to have the shape looking like this. And so in that way, I call this left end right here is our start of the base unit, and where it ends right here, because the rest is just that replication of that same base unit right there. And of course here I'm only do a hand sketch, so allow me to be off scale sometime, but this is where I call the end of our base unit. And of course, after seeing through our examples that we've done quite a few times with the examples on the transformation, even though we have not learned all of the details about the transformation yet, and you can see that the center line is running right through, horizontally right through the wave here, and the shape of the wave, of the sine wave, fundamentally on the basic units here, on the base unit, is to be waving up first. From start it waves up and it hits down about midway. So we have start, we have end, and right here it's about halfway or midway. and it crosses that center line, and then it hits a bottom peak down, and comes back at the end point. And so that's fundamentally the structure that should now have in anyone's impression about the base units of the sine graph. When it's the graph of the cosine function, so cosine of x right here, then the base unit is actually a wave like this. It's still a wave, but our base unit is going to look like this. What you need to have it in your own impression is that it's a wave unit that goes almost like a V shape. So the replication, when the replication happens, then it's going to bring us into the complete wave like this. That's what happened when we infinitely replicating that one base unit right here. But as far as focusing on one base unit of the cosine function, that's how it looks. So it actually start out so the start point of a cosine base unit is here. So it starts there, and this is where it ends here. So it starts high, and it drops down, go all the way down, hits a bottom peak, swing back up, and end at the high points again at another high peak. And so now at this point we can clearly see once again through my hand sketch version that the center line on our trig graph running through horizontally through that about halfway vertically like that. And so once again, right about halfway of our period interval on this cosine basic units right here, then it's this point right here. I call that it's the halfway right here. And so on cosine, fundamentally to remember, it looks almost like a V, but a nice curly V, a waveform curly V shape right here, and then it hits a bottom peak right exactly at halfway throughout the entire interval. And so it starts with a high, and it also ends with a high point like that. But that's where it starts, that's where it ends. Again, back to the original standard sine of x function. So with this sine of x function, what we have learned, it has amplitude being 1, the period of each units is the 2 pi interval. It has a center line at y equals 0. But now blend it together with what I've talked earlier about the start and the end of the base unit. Then so specifically on this sine function, the base unit has a start, as that start at the value x equals 0. As you can see from our graph right here, x equals 0. That vertical line right here is where the start of our basic or of our base unit on the sine function. And so furthermore, we've also learned that the base unit has an end right here, and that end right there is that value x equals 2 pi. I am now going to leave this information on our standard original sine of x here, and of course we're only studying on the base unit from now on, and then the rest of the complete graph is going to be drawn as the infinite replication of this from the base unit. So now I am going to see how I can find the graph or sketch the graph or find the graph of the function y equals sine of, now I am going to introduce how about a positive constant, positive coefficient, but multiplied with x right here? So sine of positive 2x right here. So the idea, generally speaking, what I'm doing now for now is I'm introducing that function sine of, and I'm putting in some coefficient a with x right here, and that's generally the form. And for now, it looks like what I did here is I used a being a. Let's look at a, assuming a is always a positive value. All right, so looking into our decimals device right here, then when a equals 2, a positive value, a itself being a positive value, so a equals 2, and we're going to look at the graph specifically for sine of 2x, then, and I'm still going to purposely put the graph of the original sine of x in red right here. So this is the standard original sine of x. But now sine of 2x is here, and once again in the blue version. So the shape now, that wave, that new wave being sketched, being displayed in blue right here. Let's find out how it's related to the original sine. So the shape fundamentally, the shape for one basic unit. So once again, we're only looking at the base units of the of this sine of 2x function. But on this base unit right here, let's find out some information and as well as some change compared to the original red sine of x right here. So the amplitude still remains, wave height still remains being 1. We got a center line here still on the x-axis, and eventually I'm going to write it all down. But the wave height is still 1, the same as the wave height of our original sine of x. So amplitude as a list right here, amplitude of this function sine of 2x remains the same, being 1, positive 1. The period this time has some change. Now, our red one right here for the original sine of x has a period window on the base unit right here. If we can simply look at that, the red curve has the base units with the period window, the period interval being as long as a 2 pi length right here for the period window or the period interval. But on our blue wave right here, fundamentally the shape is still the same, but it stops at pi right here. So the period here looks like it's only a pi instead of a complete 2 pi. So period for our sine of 2x here is period pi. So pay attention to that, and then we're going to have to dive in much further into that. Okay. And the center line remains the same. The center line remains the same, being on the x-axis or as an equation line, the line y equals 0. And now after we've learned about the start and the end of our base unit here, then allow me from now on, anytime we're looking at any trig function, the graph of any trig function, we are going to be nailing down the start and the end. So this blue wave right here, the base unit on our sine of 2x starts at x equals 0. Obviously the picture on the graph is showing. And it ends at x equals pi. And so it makes sense that that horizontal distance between pi and 0 is making up that period being pi right here. So before I move on to another example on this same kind of transformation, then I want to emphasize that, so the new function here compared to the original function, we put a coefficient with the x right here, so it's sine of 2x here instead of sine of x. Almost every information remained the same except for where the period is. So the period of the original sine of x, or the standard sine of x, is a 2 pi period. Here on this function, the sine of 2x, we only ended up with the period being pi. Center line is the same, start and end. And so, and I underline that with so the only information at the bottom line here, the only information when we introduce a coefficient with the x. The only information being changed here is the period information on our new graph here is being changed to a different value, and then we will nail down eventually a solid connection between how that coefficient here introduced with the x change our period. And if you can start thinking ahead of time, you're more than welcome to start coming up with that generalization here. But allow me to do another example. Okay, so how about let's look at y equals sine of 3x. And so once again, it's in that form of assuming a is a positive value, then we're looking at sine of ax right here, where a is set to be a positive coefficient. And so let's put up the graph again. The graph for sine of 3x is here, where our red one permanently being displayed here is the graph for sine of x, the original standard sine of x. So this time our wave is here. Still fundamentally it's that same shape. It looks like it's being squeezed in even more, and so we have a start, we have an end. It's a little hard to recognize this, but so amplitude, let's recognize as much as we can right here. Amplitude looks like it's the same height, the same wave height with the original sine of x. So we have amplitude 1. Period for now. The graph here doesn't have a grid that shows the period, so we will find that out. But for now, let's leave it blank for now. The center line remains the same with our original sine of x function. So it's y equals 0, the x-axis being the center line. We have the start here at x equals 0, and the ending, this is where it's making it a little bit hard to see right here, but we do have some ending. It's just not the 2 pi ending. And so as a matter of fact, this point right here, that end point right there is x equals 2 pi over 3. And so now from the start to the end, from the start being 0 to the end being the graph didn't show it, but now I'm telling everybody that the ending of this blue shape right here is x equals 2 pi over 3. And so that means the total distance from 0 to 2 pi over 3 gives us the period being a 2 pi over 3. So how do I know the period for this function is 2 pi over 3? So what I did here, the math that we did as a simple trick. Now, the rule here is that 2 pi is always the permanent period on our standard sine function. So everything goes back to the standard sine function. So the period on the standard sine function, the original sine function, is a 2 pi. I am going to divide that period of the standard sine function by 3. So think about where this 3 comes from. This 3, and provided it's a positive value, then this 3 is our coefficient in front of the x right here inside of your sine function. So that's our period here. And so generally speaking, we're going to take the period. We're going to go with the standard or just for short, our period on any function here is simply just 2 pi, the standard period, divided by the positive value, a right here, whatever the positive value being the coefficient. Okay, and so let's double check for ourselves again. But if we recall from our example right before this one right here, our little demonstration example, we had a sine of 2x right here, and we can disregard all that amplitude and center line and all that, the start point and end point. But let's look at the period one more time right here. The period for that function we have seen through the graph earlier, and feel free to roll back the video, or I'll show it here. But sine of 2x is this blue curve right here, where it stopped. The base units ended at x equals pi, which is our ending point. Our starting point is the same, and so the period was a pi, and our ending point stops at x equals pi right here. So we had an end on the base unit at x equals pi. And needless to say, the start here, even though I'm a little bit out of my order, a little bit, but x equals 0 was our start. And so, combined together with what we've just learned right here, then the reason we had that period being pi right here is simply because, once again, 2 pi is the standard original sine of x, period. But now I'm going to take that standard period, divided by our coefficient here was a positive 2, so I'm going to divide by 2. And so now it gets me doing a little bit of math right here. Our period is pi. And that's the reason, that's how it explains for this. To thoroughly understand about this kind of transformation, mainly for now, we're looking at sine of, we have a coefficient that comes with the x right here. And assuming that a is a positive value. So let me now bring up y equals sine of, how about 1/3 x, or x over 3, depending on how you want to write it. But our a value here is being a positive value, and it equals 1/3. So on my decimal graphing device right here, then this red curve is once again our graph, the base unit of the sine of x graph right here, the standard original sine of x graph. And now sine of 1/3 x is here. Alright, so the graph in blue now. Once again, what do we understand? What do we see after the observation here? The amplitude is one, just like the original sine of x. The periods, this time we can start doing some math right here, so learning, and then we can look back at the graph to confirm for here. But the periods here, think about the standard 2 pi for original sine of x, but now we're going to divide by 1/3. So let's hope that everybody is already comfortable with working on fraction, but 2 pi divided by 1/3 is the same as 2 pi times 3 over 1. And so that gives us a total period being 6 pi. And that's the reason why, let's look at our wave again. The blue wave here, it extends as far as one complete wave. There's a going up, there's a going down. That fundamental base units here going hitting up, hitting down, and cross through the center line at halfway right here, but it ends at 6 pi right here. So the complete period here is 6 pi, and that's consistent with our calculation. And so, yes, again, the center line is on that x-axis, or the line y equals 0, and our start is that famous x equals 0 start, but our ending is at x equals 6 pi. And so after I introduced that concept about the start and the end, you can see that the start and the end truly means the start of our base units, and the end here is just however it is, however far it is. That's together, from the start to the end, make that complete period window right here, that period distance. And so that is the graph of our sine of 1/3 x right here. So the more example we do, we keep emphasizing that important understanding we just learned, that the period on any of these functions is simply the standard 2 pi divided by the a coefficient value. And then we will formulate that generality shortly after a couple more demonstration examples. So what about, let's look at y equals sine of minus 2x. So we're still going to put a coefficient in front of the x inside of our sine function. But this time, notice that I had a negative sign with my coefficient. So I would see this form, so now being a little more general. The form we're looking at here is basically being, it's a minus a, because I purposely want to point out that the a here can permanently be positive. But what matters, what we will investigate now, is that what if we have so a itself is being positive, but it's a minus a with the x. So let's look at the graph this time. So this time, let's start out by looking at the graph first, so that we can see what changes, any change being done to the period, the amplitude, the center line, and all that, etc., etc. So the graph of sine of minus 2x is right here. All right, so what's going on here? So it looks like, well, amplitude, we still had a wave, but hold it, that wave will not be exactly the same wave, but wave in the end has amplitude. So the wave height right here, from the center line to the bottom peak, or from the center line to the high peaks right here, it's that amplitude 1 again. So seems like so far we have changed to a lot of different value for the coefficient inside the sine function, but it didn't change the amplitude at all. The center line this time allowed me to look at mention these things first, because it seems like nothing changed with these information. Center line remains the same, that x-axis, y equals 0 equation. We are looking at period being high. So it seems like the math here, it looks like the math here we did is that our standard 2 pi period, but remember I purposely think of the minus 2 as having a positive 2 but with a negative sign in front. So we're still going to divide the standard by the positive 2 itself right here, the positive part of that negative 2, and then we are dividing, and after dividing that, and then I'm going to explain a little shortly later that how that negative sign affects right here. But so that's how we come up with our period for this function. So period here is pi. And so in that way, you can see that the start still at x equals 0, and the ending of this base unit here is at pi. So once again, the start to the end of the period does make up that interval total period length being pi. And so now if we're looking at and comparing the two curves a little more closely, the red curve, the red graph right here is once again the base units for my standard sine of x. But the blue curve this time is the base units for my sine of negative 2x. So we track down the amplitude, the center line, the period, start and end, and hopefully everybody is having a clear, full understanding of that. But so what explains for the switched around nature? It looks like the same wave in red right here, but that fundamental shape is being reflected upside down through the x-axis. So here's my explanation. Remember we learned previously, we've learned a little while ago that sine of x is a sine function, is an odd function. Meaning, when we take sine of a negative input, which is our case right here, so remind for yourself that property on sine function. Sine function itself is an odd function. So meaning anytime we have sine of a negative angle, assuming all of these are positive, but now with the negative signs right here, and that's what negative angle is all about, then it turns out to be being an odd function. It turns out that sine on a negative angle equals to negative value on sine of the positive angle. And so this odd function property right here is being brought into our function sine of minus 2x right here. So sine of minus 2x, how we seeing this is going to be sine of 2x without the negative sign, but now the negative sign is in front. So wait a minute. So now before thinking about that negative sign right here, then sine of 2x, so this is back to that any of those earlier problem right there where we had the period change and all that here. But then the negative sign is what now explains why we have the wave. Remember we talked about m times sine of x. So anytime this m here is being a negative, so we have a negative 1 coefficient in front of the sign this time. So this is the explanation of why our wave is being upside down, reflected through. So it starts here, but it wave down first, and then wave up, and then it ends here. So this is where I would say this is where our graph is reflected through the x-axis. That's the way how we are seeing it. And now we can formulate a generalization here, a generality here, that generally speaking, starting out with letting a be a positive value permanently, then if our function is in the form of sine of ax right here, then, or if our function is being sine of a minus ax, then first what we can always remember is the amplitude remains the same, being 1 remains the same with the period, so with the amplitude of the original sine function. But period this time is changed according to this math formula. And remember, I purposely define a positive a value purposely, and so we split that down into two cases here. There's a case where it's a sine of ax, or the case of a sine of a minus ax right here. But so period can generally be the standard period 2 pi divided by a right here. That's how we find it. And the start is, of course, can do it that way. The start is x equals 0, and the end here of our function, of our basic units on any one of these functions, is x equals wherever our period ending ends at. So 2 pi over a. But now go back to this right here. Then in the special case where it's sine of a minus ax right here, then think of that as, remember that I brought in that understanding about being odd function, and we've learned that idea previously. And so this can be thought of as negative sine of ax. And so the ax, sine of ax, is having all that property here, but now having a negative in front. Now we think about the graph of sine of ax is still that similarity, having that similarity with the original sine of x. But this negative sine of ax now is going to have the graph that's wave down first and wave up, because it's reflected through the x-axis, whereas here it just stay in the original shape but with a shorter period. That's all. For the function cosine of x, let's once again have a look at the original graph of cosine of x. So this graph here, we already knew it had amplitude, being a 1. It has period being 2 pi, and so notice this is the standard cosine, and so this is what we so call a standard period. The center line we used to know, cosine is the line at y equals 0, or the x-axis. And so now with the new understanding we've learned, cosine on the base unit of our cosine graph here, the start of the base unit is at x equals 0. So just like on the picture over here, when x equals 0, we have our base unit of the cosine start here when x equals 0. And the end is at x equals 2 pi. And so once again, the same rule, the start and the end, the total distance between the start and the end is our period window, is our period, the length of the period. And so now throughout the next few demonstration examples, I am going to permanently put the information of cosine of x here on the left hand side column. And we're gonna be recognizing the properties of the other functions to the right hand side. And here we are going to investigate the case where our cosine function is having a coefficient multiplied with x. And similar to sine that we've learned previously, let's look at positive a value here. Alright, so here's our first example. Here, our first demonstration example. But let's look at cosine of, so how about 2x right here. So now I am going to bring up the graph of cosine of 2x. So cosine of 2x has the graph as following. So there's that fundamental same V shape again of the base unit. And by the way, once again, we only bring up the graph of the base unit for whichever function we're looking at for demonstration. So the red curve here is the standard cosine of x, and the blue curve is the cosine of 2x. And so it's a wave again. And so in the end, the amplitude is the same with the red curve from where the center line here is, that space, that vertical distance from the center line down to the bottom peak, or the distance from the center line, the vertical distance from the center line to the upper peak is 1. And so we have amplitude equals 1. Looking right through the graph right here, we can recognize that this base unit is being completed within the interval of pi right here, within a interval length of pi from 0 starts ending at pi right here. So this total interval length is pi. So our period on this function cosine of 2x has a period pi, and of course the center line showing in the graph, we have a center line again at y equals 0, or namely the x-axis. The start of this base unit on our function cosine of 2x is at x equals 0, and we are ending our base unit at x equals pi. And so once again, that same understanding. Period is the space, the horizontal distance between start and end of our base unit. And let's now look at y equals cosine of positive 3x. And so once again, here we're looking at a as being the coefficient in front of the x being a positive value. Let me now pull up the graph on my decimal graphing system here. So cosine of 3x is here. And so what I see here, we're looking at, it's the same fundamental shape again. The same fundamental shape. The red curve is for cosine of x, the original standard cosine of x. And our blue curve here is, it's just the same shape being more squeezed in horizontally. And so we still have that amplitude being 1, because from the center line here, the horizontal center line, that vertical distance from the center line down to the bottom peak, and the vertical distance from the center line to the upper peak right here, is now telling us that amplitude of this new function, cosine of 3x, is having amplitude 1 again. Period this time. So, looking through the graph, it's a little hard to see, but now we've learned a little bit through our study on the sine function, so it's going to behave the same. We're going to be looking at 2 pi over 3. The center line is at y equals 0. We have an x. We have a start at x equals 0, and we have an ending of our base units here at x equals 2 pi over 3. So it does look like that same generality we've learned through our investigation on the sine function. And so here similar generality right here. Our coefficient in front of the x is 3, and so it looks like from our standard 2 pi period on our standard cosine function, we are going to divide by that value a right here. And that's how it gets us our period of the cosine of ax right there. And so that's the reason how I ended up with 2 pi over 3 being my total period window, my total period interval for this function, cosine of 3x. And what about, let's quickly investigate the graph of cosine of 1/2 x, or you can write it as an x over 2, same thing. But once again, the coefficient here, even though being a fraction, but it's still in the end a positive value. So let's quickly pull up the graph here again, and I'm permanently, throughout this discussion right here, I am going to leave the original graph of cosine here being in red curve, and here's my cosine of 1/2 x right here. So this time that V fundamental shape here is stretched out further, and it seems like the interval of the period here is being twice as long right here, graphically looking. And so, and the amplitude, that vertical space from the center line to the bottom peak, and the vertical space from the center line to the upper peak right here remains the same, being 1. So we can draw another conclusion on this particular function. Amplitude being 1. Period, this time investigated graphically, we found out that period is 4 pi. And the center line remains the same, being on the x-axis, or the equation y equals 0. We have that start of the interval, of the period interval at, we start the base unit at x equals 0, and we end our base unit at x equals 4 pi. So our center line is here, y equals 0. So we start our base unit here at x equals 0, and we end our base unit here at x equals 4 pi. And so once again, let's combine with our previous understanding to see why, and to reconfirm why our periods have to be 4 pi, or in other words, let's find an explanation of why our periods for this function is being a 2 pi. So our a value is being a 1/2, that I have to write in red ink to catch your attention. And we've learned a rule, even though that rule is initially we've learned that through our sine function, but let's see if the rule applied here. So the period on this function here is, so 2 pi is the standard period of our trig function cosine here, but divided by 1/2. And so with that period, with that suggested formula we've learned through the sine function, and here let's apply it again, and it looks like we came down to and working out on the fraction right here, 2 pi times the reciprocal of 1/2, which is now a 2/1, we do end up with 4 pi. So in that way, we strengthen our understanding about the general rule of how to find a period when our trig function has a coefficient with the x with them. So let's now look at the graph of y equals cosine of negative 3/2 x. And so now we realize that we have in this function here a negative coefficient stands together with our x inside of the cosine function. However, this case right here, generally speaking, I prefer to see this as we still going to have a positive constant a right here. So the constant a is a positive value, but as being a negative coefficient, I see that as being a negative ax being inside of our cosine function. And so let's bring up the graph for cosine of negative 3/2 of x and see how it's related with our standard cosine of x that still remains on the left board here. So cosine of negative 3/2 x is here. And so once again, with the other easier information or details to recognize here, that the amplitude, first thing, wave height, the amplitude is being 1 on this function. It looks like the period here, we're looking at here. And everything for now is completely through the eyes and how we recognize through our observation. But period seems like it's the amount, the quantity being 2 pi, actually I mean 4 pi over 3. And we'll get back to that and have a better solid explanation of why it comes out being 4 pi over 3. It looks like as an estimate using our own eyes judgment right here, then it looks like this is a 4 pi over 3. And so center line on this curve in blue is the same with the original cosine, is being center line at that line y equals 0 or the x-axis. Our base unit, this fundamental shape in blue here as a base unit, has a start at x equals 0 on the x-axis and also ends at x equals 4 pi over 3. And so notice that this time we already switched to a negative coefficient. And so, but keep in mind, I explained just a moment earlier that even though it's having a negative coefficient, but I want to see as this negative coefficient as a negative sign, a minus sign with a positive constant a. And so keeping a being a positive constant, then here's how I see my period. So in the end, the actual a being positive in this case is 3/2 for this particular problem. And so let's try to apply our previous rule about 2 pi, the standard period, divided by a into this particular problem. And let's find out if it's giving us, or if it's agree with what we found through the observation right here. But so 2 pi, so in this case, consequently, we're looking at our periods for this current function is 2 pi divided by 3/2. And so doing a little bit of math here, we're looking at 2 pi multiplied with the positive reciprocal, so 2/3, and that consequently brings up 4 pi over 3, and that's how it's explained for our period for this function. Cosine of negative 3/2 of x, cosine of negative 3/2 x, the period there is 4 pi over 3. But so, what explains for the fact that this function in the end, now how about let me try to make another quick one right here, but what if we have a cosine of 3/2 x this time? Okay, and so cosine of 3/2 x is surprisingly the exact same curve. So the curve this time we didn't recognize the reflection through the x-axis, unlike the sine function. So what explains for that? So as a reminder that we already learned previously that cosine itself is an even function. So meaning, being an even function, when we take cosine of a negative expression, negative theta, it will turn out the same as the same value with the cosine after taking the positive expression. So these, and that's the reason why either we're looking at cosine of negative 3/2 x or cosine of positive 3/2 x, it's all going to turn out the same value or the same graph. And so that's the explanation why our blue curve remains the exact same fundamental, same orientations, and no flip, no reflection through the x-axis whatsoever. The orientation is exactly like our original cosine of x right here. All right, and so now we are ready to formulate that generality on cosine function of either a positive ax or a minus ax, where we permanently want to use a being a positive constant. And so what we have seen through the different graph investigations, that the amplitude of any of our function like this remains exactly the same as the amplitude on our standard function. So the amplitude on these function here is 1. The period is easily found by the standard period 2 pi, but divided by a, and that's a quick formula. Or you can use this formula. P equals 2 pi is the standard period over a, where that a was already set being a positive a. Okay, and we will have the center line being at y equals 0, and our base unit has a start at x equals 0 and has an end on our base unit at x equals 2 pi over a. And since we already knew that cosine is an even function, then take account of this evenness nature over here. So we've now learned that cosine of ax turns out exactly the same as cosine of minus ax. So in that way, graphically speaking, the two graphs are exactly the same. Either the graph of cosine of positive ax or the graph of cosine of minus ax is going to turn out being exactly the same graph. As long as we got the amplitude calculated correctly, we got the period calculated correctly, and the center line and the start and the end of the base units, and then the two graphs, the graphs of the two different expressions here should turn out exactly the same. And let's now formulate a generality for our sine or cosine function when it has that form sine of either plus or minus ax, or our function on cosine of either plus or minus ax, where our a value is permanently set to be a positive value. So anytime we have a function, our trig function being sine of plus or minus ax or cosine of plus or minus ax right here, the amplitude of these functions, the amplitude on any of these functions will remain 1, being the same as our original sine of x function. the center line will be also the same as our original sine of x function, so which is that line y equals 0, or namely the x-axis. And once again, keep that strict understanding that we're setting out a value, any of these a value being a positive value, then the period for any of our function here doesn't matter what sign be in front of the a, but the period is going to be from where our standard sine of x period, we're going to divide that standard period by a. So it's now the period on any of these functions is a 2 pi over a. And so the start of our base unit here on any of these graphs is at x equals 0. And the end of our base unit on any of these graphs here is x equals 2 pi over a as well. But in the special case when it's sine function, so special note here, but when it's particularly sine of minus ax, then the graph, in that case, the graph is reflected through the x-axis. But generally, we should understand it as reflected through the center line. Of the graph.